Hello, in this video I'm going to talk about the Fourier series for odd and even functions. Now, previously I've talked about an odd function and even function. And I said that an odd function, a function is odd if f of negative x is equals to minus 1 times f of x. And also the function is said to be even if f of negative x is equals to f of x. I've also talked about some properties of ordered even function. One of the important properties is the integral. If we integrate from minus a to a and of the integrand is f of x, which is even, then the result is the same as 2 times the integral from 0 to a f of x dx. On the other hand, if the function is odd, then integration f of x from minus a to a will give us a value of 0. Another important properties that we talked about is the products of even and odd function. One is that if we multiply an odd function with another odd function, then we get an even function. Also, if we multiply an even function with another even function, the result is also even. But when we multiply an odd function with an even function, then we get an odd function. Now, we are going to consider the Fourier series representation. In the Fourier series representation, remember we write f of x as a half a naught plus the sum from n is equals to 1 to infinity an cosine of n pi x alpha l plus bn sine of n pi x alpha l. Now, we shall be interested in these coefficients a naught, an, and bn. So we have, in the case of an, a naught, this one is defined as 1 over L, integral from minus L to L, f of x dx, while an is given as 1 over L, integral from minus L to L, f of x, cosine of n pi x over L, we integrate with respect to x. And last row we have bn, which is equals to 1 over L, integral from minus L to L, f of x, sine of n pi x over L dx. Now, our interest will be how we integrate this for the case where the function is either even or odd. So we consider two cases here. The function f of x will either be odd or even. Of course, we said that not all functions are odd or even, but we want to consider the special case, and we want to consider two such cases where the function is either odd or even. Now, the interest here is that we have some products. When computing an, we have the product f of x multiplying the cosine of n pi x over L. And when computing bn, we also have the product f of x multiplying the sine function. It is important to remember that the sine function is an odd function, while the cosine function is an even function. So once we remember this, then when we'll be multiplying, if we take a case where the function f is odd, then multiplying f of x with the cosine function, which is even, will give us an odd function. And if we are considering the case where the function f of x is even, then multiplying the function f of x with the sine function, which is an odd function, will give us an odd function, so that some of these integrals will become 0. That is the main thing, that when working with odd or even function, we are likely to know that the values of the coefficients, some of these coefficients, even before we start working out. For example, if we take the case where f of x is odd, then we'll see that integration of f of x from minus L to L will be 0. That will mean that a naught will be 0, and we will not need to work it out. We will know in advance that the value is 0. And similarly, if f of x is odd, then we will also see that f of x times cosine of n pi x, if we multiply, we'll be multiplying an odd function with an even function, resulting to an odd function, and again, integration will give us 0, so that the value of n or an will also be 0. So, then we'll come to Bn, and we'll see now in this case this will be a product of two odd functions leading to an even function, and so we can work out that. But the idea here is to simplify before we start working out. Before we work out these coefficients, we can do some simplifications. So the cash here is the product, the sine of the sine function multiplied by the function f of x, and the cosine function multiplied by the function of x when computing an. So we want to consider the two cases, and we start with case 1, where f of x is even. If f of x is even, then we see that 1, that a naught, which is defined as 1 over L, integral from minus L to L, f of x dx, will become 2 divided by L, integral from from 0 to L, f of x dx. So we can just integrate from 0, then multiply the result by 2. 2, an, which is defined as 1 over L, integral from minus L to L, f of x sine of, this is cosine of n pi x alpha L dx, will give us, again, this will be an even function multiplying an even function, giving us an even function. So we'll get 2 over L, integral from 0 to L, f of x, cosine of n pi x alpha L dx, and 3, Bn, which is 1 alpha L, integral from minus L to L, f of x sine of n pi x alpha L dx. We'll notice that in this case, if f of x is even, then we'll be multiplying an even function with an odd function, and this results to an odd function. So the integral of an odd function from minus L to positive L will give us 0. So what does this mean? That the Fourier coefficient, one of the Fourier coefficient is not to be 0 in advance. So we'll be left with a series that has the sine that doesn't have the sine terms, the series f of x will be of the form 1 over 2 a naught plus the sum from n is 1 to infinity an cosine of n pi x alpha L. So there will be no sine terms because the sine terms are 0. Sine terms are 0 in that case. Now, we consider the second case where we consider the second case where the function is odd. So case 2, we consider the case where f of x is odd. So if f of x is odd, then we see that 1, when we write a naught, which is 1 alpha L, integral from minus L to L, f of x dx, f of x is odd, this function is odd, so definitely this integral is 0. When we write number 2, an, which is equals to 1 alpha L, integral from minus L to L, f of x cosine of n pi x alpha L dx, we see that the function f of x is odd. F of x is odd. The cosine function is even. So the product of an odd and even function will give us an odd function. Integration of an odd function will give us 0. So that a naught and an are both 0. When working out bn, which is defined as 1 over L integral from minus L to L, f of x sine of n pi x alpha L dx, we'll see that here the function f is odd, the sine function is also odd, so we are multiplying two odd functions, giving us an even function. So this coefficient will be non-zero, but now we'll have 2 over L integral from 0 to L f of x sine of n pi x alpha L dx, so that we integrate from 0 to L, then multiply the result by 2. So for the case where the function is odd, see that now the series reduces to the sum from n is equals to 1 to infinity. We have bn sine of n pi x alpha L. You can see the simplification, that the knowledge of the fact that f of x is odd simply tells us that the values of a naught and an are 0. So we don't have to keep integrating the functions to find those. We only need to find bn. And that leads to some simplification of our work before we even start working out. We can know that we only need to find bn. So now, let's look at this example here. You are required to find the Fourier series representation for the function defined here. You can see that this function is defined in such a way that f of t is equals to 1 minus t in the interval t in minus 2, 0, and f of t is equals to 1 plus t in the interval 0 to 2, and the period is 4. So clearly you see that if you take t here and replace with negative t in the first interval here, you'll get if you take t in the first interval here and write f of negative t, you get 1 minus t, which is 1 plus t. And 1 plus t is basically what you have here. That tells us that the function is even. You can see they are the same sign. 1 plus t, 1 plus t. Another way we can test is by picking a value. Like we choose a value, t is negative 0.5, which is in between -2 and 0. We substitute here 1 minus 1.5 will give us 2.5. Then in the other interval, we take a value of the same magnitude. So in this case, 1.5. We substitute here, we get 1 plus 1.5. And the value is 2.5. And in that case, we see that we get the same result. And that means that the function is even. Knowing that the function is even will imply that the value of Bn is 0. So we need to find only An. We only need to find An and A0. And when working out An also, we'll not integrate from -2 to 2. When working out A0, we'll not write 1 over L integral from -2 to 2 f of t dt, so that we have 2 intervals. We'll just write, we'll just consider that because the function is even, then we only need to start from 0 as the lower limit and multiply the result by 2. So we shall write 2 all over 2 integral from 0 to 2, and in this interval we have 1 plus t. So that this simplifies our work further. So the integral of 1 plus t will give us t plus t squared over 2. When we evaluate those, we get 4. Also, when we write an as 1 all over 2, integral from -2 to 2 f of t, sorry, this is from 2 to 2, f of t cosine of n pi t all over L dt. Again, we will not need to start from -2 here because we know that our function is even. So we only need to start from 0 and then multiply the result by 2. So that we write 2 over L instead of 1 over L. And we work out. So again, because we are going to start from 0, we only have the function between 0 and 2 is 1 plus t, as we have here. So we only need to use that. We don't need the other interval now, because we already know that the function is even. Now, with that, we can now use, here we can use tabular integration to work out this. So we take the function 1 plus t here, and the other function cosine, this on this side. For this one, we differentiate to get 1, then 0. The other one we shall be integrating. And then we multiply out using these lines, and don't forget the sign, which will give us what we have here. Definitely, when we substitute t is 2, the sine term will obviously be 0. So we shall only be left with the cosine term, and we substitute 4 over n pi squared. Then we can put, then when t is 2, we get cosine of n pi, and when t is 0, we get cosine of 0, which is 1. And this, remember cosine of n pi is equals to minus 1 raised to power n. So this quantity here will be minus 1 raised to power n. So we'll be having the value as minus 1 raised to power n minus 1. And you see that when evaluating this, there will be two cases, when n is odd and when n is even. When n is odd, minus 1 raised to power n is minus 1. So we subtract 1, we get minus 2. And when n is even, this will be 1, then minus 1 we get 0. So that we only retain the case where n is odd, and we can replace n with 2n minus 1 in that case. So once we have that, we can now write our series. Remember our a0 was 4, so half a0 will give us 4 over 2, then plus an, which is this quantity, multiplying the cosine of 2n minus 1 over 2 pi t. And that reduces to this. This is the case where the function was even. So bn was 0. You can see now we didn't need to find bn because we already knew that it was 0. The second case is where the function is odd. And I'll go to example again, because I had seen that when the function is odd, both a0 and an are 0. If you look at this function and you take this interval here and you replace t with minus t between minus 5 and 0. In this interval, f of t is defined by minus 1 plus 2t. If you replace t with negative t in this interval, you get minus 1 minus 2t. We can factor out minus 1 and we get 1 plus 2t. And you see that the quantity inside the brackets here is the same as what we have here for this other interval between 0 and 5. But there is a multiplier minus 1 here, which means that when you replace t with negative t, you can see the function here is multiplied by minus 1. This will mean that our function is odd. Our function is odd. Of course, we could have taken a value, we could have used a value to test. We could have used a value to test. We can pick a value like minus 2 in the first interval, so that we substitute minus 2 here. So we get f of minus 2 is equals to minus 1 minus 4, which is minus 5. Then in this other interval we substitute 2, so we write f of 2 is equals to 1 plus 4, which is 5. We see the magnitude is the same. They are both 5 in magnitude, but they differ in sign, which means that the function is odd. This means that the function is odd. We could also use the graph as we have here, and we see the kind of symmetry we have, which will tell us that the function is odd. So whichever method we use, we find that the function is odd. And once we know that the function is odd, then we will know that a0 and an are both 0. So the only thing we need to find is bn, which is 2 alpha L, integral from 0 to L, f of x, sine of n pi x alpha L dx. The variable in our case is t, so we shall replace x with t. And notice that the period is 10, so L is 5. So we shall only need to integrate from 0 to 5. And between 0 and 5, the function is 1 plus 2t. So now so we write, using that we shall write Bn is equals to 2 divided by 5, integral from 0 to 5. In that interval, the function is 1 plus 2t, a sine of n pi t divided by 5, and we integrate with respect to t. So I'm not using x as written here because our function is defined in terms of the variable t. So now with this one, we can now use tabular integration as we have previously done. We differentiate 1 plus 2t to get 2, then we differentiate again, we get 0. Then for the other function, we integrate twice, and then we multiply out along these diagonals like shown in that diagram. And once we do that and simplify, the value of Bn is obtained. We don't need here to find An or A0 because we know that their values were 0. So we only need Bn and substitute here, and we get our Fourier series representation. So the knowledge of whether the function is odd or even can really help in simplifying our work. The magnitude of the work that you do can really be reduced by knowing that the function is odd or the function is even. Imagine this kind of a function if we did not check that it is odd. We will have started by finding the value of A0. We integrate only to find the value is 0. Then we go to An. We integrate again and find the value is 0. Then we go to Bn. So we would have worked out all the coefficients. But now, by checking and finding that the function is odd, we were able to conclude that those two coefficients are 0, and therefore we only need to find the value of Bn. So I think I will stop at that, and in the next video I'll talk about the half-range series, the half-range cosine and sine series. Thank you for watching.